The problem appeared almost immediately.
The James Webb Deep Field image came back, and instead of quietly confirming expectations, it started putting pressure on them. Bright galaxies appeared in places where many people expected far less development. The first major observation was supposed to strengthen confidence in the predictions. Instead, it created a mismatch.
At first glance, this looked like the moment everything would line up.
Webb could see deeper. Webb could see earlier. Better data should have made the picture clearer. But as scientists compared prediction timelines against what was actually showing up in the images, the fit began to break down. Several galaxy candidates appeared extremely early after the Big Bang, not a little earlier. Early enough that the expected timeline no longer seemed to match what Webb was revealing. And that changed the role of the telescope almost overnight. The mission was not supposed to create a contradiction. It was supposed to test a prediction and confirm it. Instead, the James Webb Deep Field image placed the prediction and the observations side by side, and the two did not cleanly agree. That is what made the result so unsettling. The issue was not a lack of data. The issue was that the new data immediately increased the pressure on the prediction itself. With every bright galaxy emerging from those deep observations, confidence was no longer flowing in one direction. The prediction system that seemed ready for confirmation suddenly looked vulnerable. And that left a question hanging over the entire debate. Are the galaxies wrong? Or are the predictions wrong? Then another James Webb survey field appeared. If the first result had been a fluke, this was where the pressure should have eased. A different field, a different patch of sky, a different observation. The contradiction had a chance to stay isolated. Instead, another early galaxy candidate was highlighted. The immediate comfort of calling the first result an exception started to fade. What had looked like a single strange object was now showing up again in an independent Webb field. Then it happened again. More candidate galaxies emerged across separate surveys. Each new field added another data point. Each new observation gave the same uncomfortable signal. The expected timeline was not snapping back into place. And that changed the conversation. The question was no longer whether one object looked unusual. The population count itself was growing. What began as an isolated mismatch was starting to resemble a pattern. That is what made the tension harder to dismiss. A single surprising observation can sometimes be explained away. But every new James Webb survey field carried the risk of repeating the same problem. Every new candidate galaxy reduced the statistical comfort that the first result had simply been an accident. The contradiction was no longer standing in one image. It was spreading across independent Webb fields. And with each repeated observation, the outlier explanation lost a little more ground. The telescope kept looking. More candidates kept appearing. The count kept growing beyond expectations. At some point, a difficult question begins to take shape. How many observations can disagree before the prediction itself becomes suspect? For the first time, the pressure seemed to ease. The focus shifted to James Webb spectroscopy. The images had shown what was there. Now the spectra were analyzed in greater detail, and the picture began to look less catastrophic than it had at first. At the same time, simulation outputs started changing. The observations had forced adjustments. Models that once produced slower timelines were updated. New theoretical runs generated earlier growth, and the gap between prediction and observation began to narrow. That mattered. The growing population of early galaxy candidates no longer looked completely disconnected from expectation.
As the simulations changed, predicted populations moved closer to the populations Webb was actually finding. Suddenly, there was a believable answer. Maybe Webb had not broken the prediction at all. Maybe the problem was simpler. Maybe galaxy growth had been underestimated. That idea carried real weight because it matched what people were seeing. Webb spectra were being analyzed. New measurements were arriving. Updated simulations were producing earlier growth. Different pieces of the picture were starting to point in the same direction. The contradiction had not vanished, but it looked smaller. And that changed the mood of the debate. Instead of asking whether something was deeply wrong, it became possible to imagine that the system was doing exactly what it was supposed to do. New observations arrived, models adjusted, predictions improved. The disagreement shrank. The crisis appeared manageable. Confidence returned, but in a different form. Not confidence that the original prediction had been perfect, confidence that the prediction could be repaired. For a moment, that seemed like enough. The observations and the simulations were moving closer together. The question was no longer whether a fix existed. The question was whether the fix would hold. Then the spectroscopy arrived. The final filter was removed. Look at JADES-GS-Z140. It sits at a redshift of 14.3. That means its light comes from less than 300 million years after the Big Bang. Inside the cosmic dawn. A galaxy this early was supposed to be small, fragile, and chemically young. Mostly the first raw material. Mostly hydrogen. Instead, Webb revealed something too developed for that simple picture. JADES-GS-Z140 stretches roughly 1,600 light-years across. It is bright. It is structured. And later observations found oxygen in it. That detail changes the problem. Oxygen does not appear first. It has to be made inside stars. Those stars have to live. They have to die. They have to explode. Then they have to spread that material back into space. So this was no longer only a question of fast galaxy growth. It was a question of history. The temporary fix had been simple. Maybe galaxies formed faster than expected. But speed alone no longer solved the whole problem. Webb was not just showing a galaxy that appeared early. It was showing a galaxy that already carried signs of chemical maturity. The correction moved the contradiction. It did not eliminate it. Every surviving object now asked a harder question. If faster growth cannot create that much history in less than 300 million years, then what can? For a while, the pressure seemed aimed at one assumption: galaxy growth. That was no longer true. A galaxy can be revised. A timeline can be adjusted. A simulation can be updated. But JADES was creating pressure in several places at once. The age, the brightness, the chemical maturity. The assumptions were no longer failing one at a time. They were starting to overlap. And that changed the scale of the problem. The debate was no longer about explaining one galaxy. It was about understanding how many assumptions had been supporting the prediction all along. That is the part of the story Webb ultimately changed. The telescope did not slow down. Field after field, measurement after measurement, the evidence kept improving.
But the dependence on assumptions did not disappear.
It became easier to see. A model is not just a prediction. It is a machine built from what scientists choose to treat as settled.
Webb did not break the universe.
It broke the machine. The original deep field image now means something different.
The question was never only whether Webb had seen enough.
The question was, what had been assumed before Webb ever looked? Better tools did not create certainty. Better tools exposed where certainty had been borrowed from assumptions all along.